Hey, I am live on YouTube and I am live on Twitch, it seems. Yep, you are live. Seems. Yep, you are. Yep, and it's not lagging, right? Oh, nope, doesn't seem to be. Yep, and um, on YouTube, yes, I am live. Now, for today, modern assembly language. Um, Yesterday, we completed chapter 3, load, store, and branch instructions. We read about instructions and then did chapter summary and then the exercises, which were good. We also wrote a few assembly programs. And now, moving on to chapter 4, data processing and other instructions. Page number 83. Let's go. Technoblade never dies. And yep, here we are. Data processing and other instructions. The AArch64 processor provides a rich set of data processing instructions, most of which perform arithmetic or bitwise logical operations. There are also a few special instructions that are used frequently to perform operations that are not classified as load, store, branch, or data processing. There are a few special instructions that are used infrequently to perform operations that are not classified as load store, branch, or data processing. Okay. The data processing instructions cannot access data stored in memory. They operate only on CPU registers and possibly immediate data that is encoded as part of the instruction. Okay, immediate data that is encoded as part of the instruction. The instruction itself contains the data. In general, data must first be moved from memory into a CPU register before processing. Processing can be performed. The most common way to move data from memory into registers and vice versa is by using the load and store instructions, yes, which are covered in chapter 3. Yes, and each data processing instruction performs one basic arithmetic or logical operation. Okay, arithmetic or logical operation. The instructions are grouped into the following categories: arithmetic, plus minus multiply divide, logical, and or data movement. The instructions are grouped in the following category: data movement, load, store, okay, or move, or multiplication, division. Arithmetic is not does not contain multiplication and division, it seems. Comparison, greater than, less than, it is could be considered logical. Conditional, if then, and special. Operand 2. Most of the data processing instructions require the programmer to specify two source operands and one destination register. Because three items must be specified for these instructions, they are now known as three address instructions. The use of the word address in this case has nothing to do with memory address. The term three address instruction comes from earlier processor architectures that allow arithmetic operations to be performed with data that is stored in memory rather than registers. Okay. Referring back to figure 3.1, the first source operand specifies a register whose contents will be supplied from the register file on A bus and enter the ALU. The second source operand will enter the ALU through the B bus and okay, wait. How can I open a new tab with the same thing? How to open a new tab in Chrome with the same URL. What is the shortcut? Control Shift T or Command Shift T on Mac. Command Shift T. Shit, that is just to open the same URL as the current tab. Now Okay. Um, okay, 3.1. Mm, in the starting before load store instructions, and yep, here we are. Yeah, it says that it is said that, referring back to figure 3.1, the first source operand specifies a register whose contents will be specified from the register file on A bus and enter the AL. The first source operand specifies a register whose contents will be supplied from the register file on the A bus and enter ALU. A general purpose. Okay, the first source register, source, not the destination, source register. Uh, the content of the first source register will enter the ALU through this A bus, and then we move on to the B bus. Okay, enter the ALU. Okay, the second source operand will enter the ALU through the B bus and will either be the contents of a register on a or an immediate value which is encoded in the instruction currently being executed. Okay, the second value will come through the B bus, and it can either be the contents of a general purpose register or any register, or it can be an immediate value which is encoded in the instruction itself which is being executed. This second operand entering the ALU is referred to as operand 2 and can be one of four things. Okay, a register, R0 to R30, a register and a shift operand to modify it. Makes sense. A register and a sign extended operation that also shifts the register left by 0 to 4 bits, or a 12-bit immediate value. Okay, a 12-bit immediate value. What is 12? How much? It can be signed, right? If it is signed, then 11 bits will be used to store data. And if it is that, then the range would be from minus 248 to from minus 249 to plus 248, a 12-bit immediate value. The operations for operand to allow a great deal of flexibility. Many operations that would require two instructions on most processors can be performed using a single AArch64 instruction. The table 4.1 shows all the possible forms of operand to immediate value operand. This is called the second one. The value that comes into the ALU through this bus B is called operand 2, and operand 2 can be a immediate value, a 12-bit immediate value, pattern, when that is new, a pattern, a 13-bit pattern immediately used only for logical instructions, only for logical instructions. Okay, RM, nth register, any of the 31 registers, RM shift, and then the register and shift, and how much shift. Okay, the contents of a register shifted or rotated by an immediate amount between 0 to 64. 64 is the maximum, is the number of bits. If you shift it by 64 bits, you cannot shift it more than 64 bits, because what will you get? You will get nothing, zero. And now, RM extended OP. How do you want to extend it? And what does it mean to extend? The contents of a register are extended and then are shifted left by 0 to 4 bits. Note that this mode cannot be used with logical instructions. Extended. What does it mean to extend the contents of a register? What does it mean to extend the contents of a register in Assembly language. Ah, why is this not okay? Copy, refresh, and yep, as function yet yes. In assembly language, extending the contents of a register refers to converting a value stored in a smaller bit width register, example 8-bit or 16-bit, into a larger bit width register. This this process is used to ensure that the value in the smaller register can be interpreted or processed correctly when operating in a larger register context. There are two primary ways of extension. Zero extension fills the upper bits of the larger register with zero, makes sense, used for signed values to prevent their magnitude, to preserve their magnitude during the extension. Makes sense? Example, ARM64, UXTB, extend TB, unsigned, extended byte, unsigned, unsigned, extended byte. Okay, extends a 8-bit value to a 32-bit or 64-bit register by filling up the upper bits with 0. Move FF is like, okay, a 8-bit value, a single byte, and we move that into 32 bits. Then we extend the contents of W0 and put them into W1, extended W0 to W1. Okay, that makes sense. Sign extension fills the upper bits of the larger register with the sign bit of the smaller value, the most significant bit or MSB, used for signed values to preserve their sign and magnitude during the extension. Okay, signed extended bit, extend bit, byte extends a 8-bit value to a 32-bit or 64-bit register by filling the upper bits with the values of the most significant bit. Okay, whatever is there, then it should result in 111. Shit, FFF, because the most significant bit here is F. F means 1. So yeah, FFFFF. F means 1. A single F represents 4 ones. That is 4 ones, right? Yep, 4 ones. That is 15. Why extend the contents? Compatibility, correctness, efficiency. Okay, UXTB, STB. Right. Now we can extend and then shift. That is crazy. Okay, if I use a smaller register here, a register which has a smaller value than the destination register, then the destination register, then that value will be extended according to this and then shifted according to this number. Makes sense. Now, shift and rotate operations. Table 4.2. This table 4.2 shows the mnemonics used for specifying shift operations, which we prefer as shift OP, shift operations. All of the shift operations required for the require the programmer to specify a shift amount, which we will refer to as n. The LSL operation, left shift operation, which shifts each bit left. 0 is shifted into the insignificant bits, and the most significant n bits are lost. Okay, 0 is shifted to the n least significant bits. Number will go left, and the least significant n bits will become 0, and the most significant n bits will be lost. The LSR operation shifts each bit right. LSR, LSR, shift right. L, what is L? Shift left. And what is L here? L, shift right operation shifts each bit to the right. And if we are shifting by n, then the most significant n bits will become 0 and the least significant n bits will be lost. Let's see. 0 is shifted into the n most significant bits and the least significant n bits are lost. What I said. And the ASR, okay, a shift right operation shifts each bit right. LSR operation shifts each bit right. ASR operation shifts each bit right. The n most significant bits become copies of the sign bit 63, become copies of the sign bit 63 and of the sign bit 63, and the least significant n bits are lost. Okay, so instead of coming 0, getting 0 at the most significant bits, I will get what whatever is the sign bit. The ROR operation rotates the bits to the right. The n least significant bits become the most significant bits, and all other bits are shifted right by n. Okay, the rotate ROR operation can only be used with bitwise instructions and such as AND or move and test. This cannot be used with arithmetic instructions such as add or compare. All of these instructions will be covered later in this chapter. Okay, lesson logical left shift. L means logical left shift, then logical right shift, then arithmetic shift right, arithmetic shift right, rotate right. Bitwise instructions only can use this operation. Okay, so there is instructions and these are operations that can be performed on the values that are being used in that instruction. Extend this table 4.3, this. Okay, left shift to shift left normally, logical shift left, and then we have logical shift right to logical shift right, and then ASR, which loses the least significant n bits, but the most significant n bits become same as the sign bit. And then we have ROR, rotate right, which is the least significant n bits become the most significant n bits, and every other bit is shifted to its right n times, to its nth position. Table 4.3 shows the mnemonics available for the extension operations referred to as extend. op- there is an extension for each size. Okay. Double word, word, half word, and byte, which can be signed or unsigned. Unsigned extension is the same as zero extension, fills the higher bits with zero. Fills the higher bits with zero. Signed extension copies the bit into the higher bits. Note that the two extension operations are always redundant depending on the size of the register specified. For example, signed extension and unsigned extension TX. I don't know what TX is. TX. TX double word. X is double word. TW is word. TH half word. TB byte. Logical left shift. We can use logical left shift. Yeah, we can use logical left shift to extend. Now unsigned extension, extension XT and to a byte. The thing will become a byte long. Unsigned extension to a half word that is 16 bits, and unsigned extension word that is 32 bits, and unsigned extension double word that is 64 bits. Makes sense. Now, um, yep, for example, signed extension for 64 bits and unsigned extension for 64 bits are redundant for 64-bit registers. Okay. However, if RM is a 32-bit register WM and XTW, okay, if we are performing these extend operations on a register which is already that size which we want, then it is redundant because what will it do? There are no empty bytes to fill, empty bits to fill. However, if RM is a 32-bit register, then XTW and signed extension word and signed extension unsigned extension word are redundant. In each of these cases, the unsigned extension is always preferred. If the shift immediate amount is not zero and the extend OP is redundant, then left shift mnemonic. If the shift immediate amount is not zero and the extend OP is redundant, then left shift mnemonic should be used as the extend OP for clarity. Makes sense. Extension cannot be used with logical instructions which are able to use right shift, right, rotate, right. Wait a minute. Yes. And my voice is reduced and is it fine now? It is fine now. Now, extend operations. Yes, we did this, extend operations, and now immediate data. There are two types of immediate values, 12-bit, unsigned, immediate. There are two types of immediate values. Yes, 12-bit unsigned immediate makes sense with a range of 12-bit unsigned. Yeah, it starts from 0 and goes up to 4095, not to 4096, and 13-bit pattern immediate. The first immediate is used for every instruction type that is not logical instruction. The first immediate is used for every instruction type that is not logical instruction. Okay, logical instructions are use pattern immediates which were introduced in table 3.3. Pattern immediates which were introduced in table 3.3. The first immediate is used for every instruction type that is not logical instruction. Okay, the first immediate is used for every instruction type that is a lot bigger. Okay. The first immediate is used for every instruction type that is not logical instruction. Yes, makes sense. Logical instructions use pattern immediates, which were introduced in table 3.3. When choosing a pattern immediate, only values that can be especially encoded in the 13 bits are valid. When choosing a pattern immediate value, a bit pattern of consecutive ones must be used. This pattern is then repeated and either this this pattern is then repeated either this times across the register. This or this times across the registers and it may also be rotated. For example, the immediate 5 would not work because it's binary representation. This why is 5's binary representation this? Oh, 0b means binary and 101. Okay. Is not a consecutive pattern of ones. Would not work because this representation is not a consecutive pattern of one and a consecutive pattern of oh, no, 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 hexadecimal. a woodwork for a 32-bit WN nth register. An immediate value of 7 is valid because it's a binary representation. 0 triple one is 1 is 3 ones in a row. Furthermore, 7 can be rotated to create 700, which is also valid. Hmm. Yeah. This is not making a lot of sense, but I see there are two types of immediate values. Okay, the immediate value that they are talking about is this shift immediate value that signifies the amount. Oh, is it the shift immediate value or the immediate value that is provided uh, for the operation? Yep, it is the immediate value that is provided for the operation itself, not the immediate value for the shift. Okay, yes. Okay, there are two types of immediate values: 12-bit unsigned immediate with a range of this and 13-bit pattern immediate. The first immediate is used for every instruction that is not a logical instruction. The first immediate is used for every instruction that is not a logical instruction. Okay, this one, this value, 12-bit value, is used for every instruction that is not a logical instruction. And logical instructions use pattern immediates which were introduced in table 3.3. I don't know, table 3.3. What was introduced in table 3.3? Where is the table 3.3? 3.2, 3.3 pattern summary of valid immediate value. Okay, 12-bit pattern immediate series of ones or more ones followed by one or more zeros is repeated as an element 1, 2, 4, 8, 16, or 32 times to fill the register and may be rotated. Okay, pattern immediate series of one or more ones followed by one or more zeros is repeated as an element is repeated is repeated as an element 2, 4, 8, 16, or 32 times to fill the register and may be rotated. That makes some sense. This is valid because F0, what is F0? F0 is 4 ones and then 4 0, 4 ones, 4 0. So at the time of extending, we would fill it with 4 ones, 4 0, 4 1, 4 zeros. Is that it? And this is not valid because 4 ones, and then what is E? ABC. E is 4 ones, 1 0. And then we get E again. It is not a good pattern. Okay. Logical instructions use pattern immediates which were introduced in table 3.3. When choosing a pattern immediate, only values that can be specially encoded in the 13 bits are valid. When choosing a pattern immediate value, a bit pattern of consecutive ones must be used. This pattern is then repeated either 1, 2, 4, 8, 16, or 32 times across the register, and it may also be rotated. For example, the immediate 5 would not work because its binary representation 101 is not a consecutive pattern of ones. A consecutive pattern of 101 hexadecimal list would work for a 32-bit register. An immediate value of 7 is valid because its binary representation 111 is 3 ones in a row. Furthermore, 7 can be rotated to create 700. This This is not 700, this is hexadecimal 700. And okay, which is also valid. Okay, okay. Data processing instructions. The following instructions use the ALU to perform arithmetic and logical operations. Most of them require two source operands and one destination register. However, there are some exceptions. For example, the instruction for calculating the 2's complement only requires one source operand, and the comparison operation does not require a destination register. Most of these instructions have an optional S modifier which allows the programmer to choose whether or not the instruction will affect the states in the P state register. Okay, S modifier. And will affect or will not. And I don't know. Add, add, add with carry. Okay, add and give me the carry, and the carry will be stored in the P state register. That is beautiful. And subtract, subtract with carry. The carry will be stored in the P state register. Negate and negate with carry. Okay, let's see. All of the non-carry instructions involve two source operands and a destination register. The carry instructions may only use unextended registers as operands. Carry instructions may only use unextended registers as operands, because if you shift or extend them, then they might not produce the carry. I guess. RD, what the heck is RD? Destination register, destination register, and number and operand 2. OP2, um, S or S not. Okay. OP is one of add or subtract, and add and subtract have this destination register. One, so first source register and then the second operand, which is called operand 2. OP2 is one of add carry, subtract carry. The carry bit from P state is added to the two operands. The carry bit from the P state is added to the two operands. Okay, the carry bit from the P state. So the carry bit in the P state as it was before the this instruction was called, or the carry bit that is um, is produced by these instructions. Negate and negate carry are aliases for sub and subtract carry where Rn is 0. Therefore, neither syntax uses Rn. Okay, neither syntax uses Rn. Okay, so negation is just getting two's complement for the thing, right? Negation and negation is carry because I am subtracting from 0 the thing, so I get it's negative. The optional S specifies whether or not the instruction should affect the bits in P state. Makes sense. Yes. Add, what does it do? Rn, Rn plus operand 2. Save that into the destination register. Add with carry Rn plus Rm plus the carry that is already stored in the P state register. Now subtract. Subtract from Rn operand 2 and save it to the destination register. And subtract with carry. Okay. carry, subtract, subtract, subtract from Rn the value of Rm, and then add carry. If carry is 1, then nothing is subtracted, and if carry is 0, then 1 is subtracted. Okay, negation. It just adds the negative, gives the 2's complement for the operand 2. Okay, now negation with carry, negative of the number, and this add this value to it. Okay, add this, add the contents of the x1 register to the contents of x2 register and store the value in x0. Subs Subtract the contents from the contents of x3 register, subtract 1 and save the result in the third register, and also update the program state, p state. Now negate, find the negative for the value at, no, find first, take the value at the x5 register, and then logically shift it left by 4 bytes. That is equal to multiplying it by 8. Yep, and then find that value's negative and store it into the fourth register. Yep. Example 9. The following listings show a complete program for adding the contents of two statically allocated variables and printing the result. The printf function expects to find the address of a string in x0 as it prints the string. It finds the deformatting command, which indicates that the value of an integer available should be printed. It expects the variable to be stored in w1. Note that the variable sum does. Okay, it expects the variable to be stored in w1. The variable to be stored in w1. Yes, w1. W1. Note that the variable sum does not need to be stored in memory. It is stored in w1. Okay, where printf expects to find it. Okay, that makes sense. Static x is this, and static y is this. I declared two things, and they are static. That is, they are not accessible from outside this file. Now there is an integer called sum, and sum is the sum of x and y, and then print and return with 0. FMT format string is this, the sum is this, align it at 2, and in the data section itself, make a label x, which stores a word, that is 32 bits to store the value 5, and another label y, which also uses 32 bits to store the value 8. Now in the text section, there we have a label whose type is function, and let's make the main label global so that it can be accessed from outside. Now in the main label, store the address starting from this command. Store pair. First, store the frame pointer and the link register contents into the stack. Now find the sum. For the sum, we first get the address of x into the 14th register and the address of y label into the 15th register, and then we load. Yes, after getting the address, we load the content at the memory cell whose address is in the 14th register. We store that value into the fourth, and in the fifth register, we store the value of the memory cell whose address is at the 15th register, which is the y label. And then we add the contents of the fourth and fifth register and store the value in the first register. Then printf, the sum is this. We want to implement this thing, and for that we get into the zeroth register, the address of the first character in the format string. After that, we call the printf because we have both the arguments. In the first zeroth register, we have the address for this string, and in the first register, we have the value that will be that will replace the %d sign. Now return 0. Uh, we want to return 0. We move the value 0 in the zeroth register and then load back the frame pointer and the stack point and the frame pointer and the this link register contents from the stack pointer, and then increment the stack pointer by 16. That is just popping. Then we return. That makes sense. Wait, why do I have this here? Now this is from yesterday. This is also from yesterday. Chapter 4 Rhodes. Nope, there is supposed to be chapter 4. Not not global. Wait. In the data section, we define a string which ASCIIs, which stores the ASCIIs value, which is the sum is %d, the new line, %d new line, and yeah, that is about it. Yes, that is about it. I would need, and then I store a label x, which stores a word, and the word's value is 124, 1234. And then I have another label which also stores a word and whose value is 4321. Yep. And then in the dot text section, I declare, and thus I declare, I align by 4 bytes, that is 2 power 2 is 4, and then I make a global label which is accessed, which can be accessed from outside, and then I just define that label. And what does the label contain? Label first stores the frame pointer and the link register contents. So let's just do that. But we don't actually have to do it, but let's be good people. And stack pointer, no, store pair the contents of x29 and the contents of x30. And where do I want to store them? I want to store them at the location of the stack pointer minus 16, and that is a pre-increment. After doing that, I need to get the address of x and y and string. Well, I will get the address of string when I call the printf function, but first I have to get the address of x and y. Address of the page, address of the page will be stored in 14, and yep, address of the page for the X register. And now to add, I want to add to the 14th register the contents. I want to store in the 14th register the sum of the 14th, the value at the 14th register, and the page offset for the X label. Now I have the address of X. Now the same thing for the Y label to store its address in the 15th register, X15, and add to the 15th register in the page offset. Now I have the address. Now I have to load the values and LDR or yeah, LDR. I can actually do. Wait, I didn't had to get the store the values of these because I have uh, these two labels are stored one after the another, one after another. So if I have in the 14th register the address for the X label, then I know that the address after 4 bytes is the starting address for this label. So I can actually just load pair into the third, let's say, and into the fourth register, and the address starts at whatever is the address in the 14th register. That should do. And I have to tell that the address boundary is a word. So LDPW, how to tell that it is a word? Well, this is good. Just using W there to tell that it is a word that I want to store. Like word, not a double word, which is 64 bits. Now I need to store the sum, the addition into the, let's say, first register and add the contents of the third and the fourth register. And yes, now I have, now I need to get the address for the string into the 0th register to pass on to the printf function. For that, I need to get the address page into the 0th register for string page. That is how I get it. And store into the 0th register the sum of the content of the 0th register and the page offset for the string. Cause I'm a man, woman, that makes sense. Okay, and we saw yesterday that to pass on to the second argument, which will replace %d here in this string, we have to add it to the stack pointer. So, so store the contents of W1, that is the sum, store the sum that is stored in the W1 register at the address of the SP, at the address of the stack pointer. And I can like literally mess this up quite a bit, but and then yes, I have provided the string in the 0th register and the value to replace the %d in the at the stack pointer, and then I just call branch link um printf, and after that I have to clean up the mess that I created. That is why by first loading into the X29 and in the X30 register the contents of the stack and then increment it by 16 afterwards. Yes, and is there something else? Yes, I would like the program to end, to return with a 0 code, that is move into the zeroth register, the value 0. Zeroth register is the return value of a function, and then just return gcc chapter 4 dot s and out dot slash out. What will I see? I should see 5. The sum is 5, 5, 5, 5. The sum is 5, 5, 5, 5. But why did it take so much time? Yes, okay. So this function is working as function yet. Now, logical operations. Wait, what the heck? Multiply with 128 bit results. That is 64 bit number into 64 bit number. That is crazy. The program is long. Well, it is in assembly, so yes, it is long. Should we are still at 4.2 conditional operations? Hmm. Well, seems like we won't be able to finish this chapter today. And then at the end, we have special instructions, something very special. Okay, and then we have alphabetized list of AArch64 instructions. Instructions that we have read, that we have been told till now. That is good, right? Right? Okay, how many different forms of add are there? Add, just one, no, two. Add and add with carry. Okay, and for branch, I see, I see. Branch link and register. Uh, Let's go back, go back, go back, go back. Mm. Yes, logical operations. There are 7 basic logical operations: and, bitwise and, BIC, that is bitwise, bit clear. So just clear the bits. Bitwise XOR, bitwise X or not, or exclusive or XNOR, bitwise XNOR, XNOR, and bitwise or, bitwise not or not. Okay, exclusive not, or not. Moving bitwise not. We don't make any sense there in not. Okay, all of them involve two source operands and a destination register, except for MVN, which requires one source and one destination register. Yes, destination register and a source. All of them like this and this. And they can be stored, they can be configured to update this program state. Now, OP is either AND or BIC. Okay, and BIC are the only instructions that can update the program state register. Okay, and BIC, bitwise, bit clear. Okay, and then we have OP2 is one of XOR, XOR not, or not. BIC, that is bitwise clear, or MVN, somehow means not. The optional S specifier whether or not the instruction should affect the NZCV flag bits in the P state. Yes. Recall from section 4.1 that operand 2 may use the ROR shift and no sign extension. And no sign extension. No sign extension is unsigned extension. That is just adding zeros at the front, or ROR, just the least significant n bits will become the most significant n bits, and every other bit will be right shifted by n. Now, operand 2 may only be used as an immediate in the following cases. May only be used. Okay, so operand 2 can only be immediate values when we are using the ands instruction, or exclusive or instruction. Okay, MVN is an alias of ORN or not, where or not, this or not for zero register, where RN is zero. RN is zero. Okay, and add not. Okay, okay, add not of this thing. Bitwise, bit clear, bit clear. This is called a bit clear. Okay. Find the and of this thing and with the not of this thing. Okay. Exclusive or, exclusive of Rn and operand 2, exclusive or not for Rn and not operand 2. Not operand 2. Okay. Or not, or not. Okay. And then not. Okay. This is not making a lot of sense because or not is supposed to be a not of this whole thing, right? Or not is supposed to be the not of this Rn or operand 2. But here it is this way. So okay, let's work with that. Find the and of this and this, and store the result in this, and also update the program state. Set p state. BIC, that is quite a bit of number. Store into the third register the uh, and of this thing, and the and of this thing with the value which you get after finding the not of the value after shift the value in the fourth register left by 5 times, that is multiplying by 32. Find the not of it and get its and with the contents of the third register and save them into the third register. Yes, that is what it is written here. Exclusive or, yes, find the exclusive or for the value at the fifth register and this thing, and store it into the fourth register like this. Data movement operations. Yo, the data movement operations copy data from one register to another. Move with wide with zero. Move wide with zero. Move wide with not. Move wide with keep. Okay, keep as in her give, give, give. The move instruction is an alias chosen by the assembler for or moves move. Okay, and or add instructions. It facilitates choosing an immediate value or moving a register value to or from the stack pointer. The wide moves allow the programmer to widen the 16-bit immediate value to fill a 32-bit destination register. Okay. Hmm. It actually seems really bad when I rotate water in my mouth. Okay, so bitrate was very low at one point, but now it is fine. And live on YouTube also seems to be fine. Okay, it has a thumbnail now. It's too quiet, but okay, it's okay. I'm a cyborg, but it's okay. OP is one of the wide moves. Wide moves. So wide is just the wide moves allows is just like extend. The wide move allows the programmer to widen the 16-bit immediate value to fill a 32-bit or 64-bit destination register. OP is one of the wide moves. Okay, any of these. It accepts a register and the value with which it is supposed to find the operation with. Yes, the value that is supposed to be moved, and then left shift, left shift by this much shift. Okay, okay, but I won't. It will break your heart. It accepts an optional shift of either 0, 16, or 32-bit or 48-bit for a 64-bit register. 48, why would I want to shift for 48-bit when I have a 16-bit value? Then I would like to shift my value 48 bits to make my bits, my 16 bits, the most significant bits that ever existed. Right? For a 64-bit destination registers or a shift of 0, 16 for 32-bit destination registers. Non-pattern immediates are wide, 16-bit long. Any 64-bit value can be loaded with 4 move with the 4 move. Why would I need 4 move? 64-bit because 16-bit long. Okay. Non-pattern immediate values are 16-bit long. Okay, so immediate value in here can be 16-bit long, and if they are longer than 16-bit, then they won't be able to be, then they won't be stored in the instruction, right? Then they would have to be stored in the literal pool. Any 64-bit value can be loaded with 4 move and oh, just keep, which means I think that keep the original 1 bits and write this value, the new 16 bits that we are providing over the last value. If a pattern, if a pattern, if it is a pattern, it can be done with just one move instruction, which is an alias for or. If it's a pattern, it can be moved with just one move instruction. This move general purpose register to a from SP or to from another general purpose register. continue to next page. Okay, thanks. Move. Move an immediate value or pattern into the RD register, destination register. Move a value into after shifting into this register. Move a value after shifting and then finding the not for it into the destination register. And then move the value into after shifting this value. Move add the value this here. Shift if I shift by 2 times, let's say, multiplying it by 4, or let's say 16 times. If I shift 16, then 15, what is semicolon? Sets only 4 bits and keeps the rest of the numbers. Sets only 4 bits or bytes. 4 bits and keeps the rest of the number. Let's see. Move the contents of this into this. Okay. Move the contents of x3 into the stack pointer. Then move this behemoth into the zeroth register. Then move into the zeroth register. The value of z is like moves. What is the full form actually? With zero left shift this number by 48 bytes and store it in the zeroth register. Then keep. Okay, that makes sense. Okay, first I move into the zeroth register this value, right? This takes 1, 2. Okay, how 2 bytes. This takes 2 bytes, right? I get 2 bytes, 2 bytes here. No, yeah, 2 bytes. 2 bytes first stored, then 2 bytes, then 2 bytes, and then 2 bytes. Therefore, I successfully stored a 8 byte value. Now I first take this value, left shift it by 48, then I move the contents into the zeroth register. This uh, after left shifting this value by 32, and then I left shift this value and move it into the zeroth register, and then I move into the zeroth register this value. Shift operations, that is a good way. Shift operations. The shift operations allow the programmer to shift or rotate the contents of register Rn by the number of bits given by the contents of Rm. So this is just pure shifting operation. Shifting operation. This is not like some conditional, not conditional, but optional aim shifting using an immediate value. There are 4 operations: arithmetic, shift right, logical, shift left, rotate right, RO, rotate right. Okay. Syntax operation, that is opcode. Op is one of ASR, LSL, LSR, and roar. Roar was a good movie, which is about the tigers in the Sundarbans. When shifting right, the programmer must decide what to do with the most significant bit. Hmm. What to do with the most significant bit when shifting right. Okay, and arithmetic right shift means that arithmetic right shift means that the most significant bytes will become the same as the most significant byte before the shift. That is, if it is a negative number, then the n most significant bytes will become 1. But if it is a positive number, then the n most significant bytes will become a 0 with ASR, arithmetic shift right. An arithmetic shift right, right shift means that the sign bit is extended to fill the upper bytes, whereas a logical right shift uses zeros to fill the upper bytes. The register RM's value the register size the register size 32 or 64 is used as the shift amount. The rotate right operation rotates n bits to the right. N bits to the right. Those bits wrap around and are shifted into the upper bits and become the most significant bits. Left logical left logical shift left logical shift right arithmetic shift right ROR roll lesl lesser asr roar. Okay, right shift by the amount of RM. Same here sign extended. Yep, sign extended. And here thing lesl asr lesser roar. Shift the contents of this by the value that is stored in this. Yo, these instructions are redundant. Mm, because the same results can be achieved with an add uh, or and instruction. For example, let's say that I add into the zeroth register the contents of the zeroth register and the value in the zeroth register by left shifting it this much times. Makes sense. Or I can get an or. So it is redundant, but like it is not that I'm doing the same thing twice. Right? You are saying that there are other instructions which can be used to achieve this same result. Although the results are identical, use of the LSL, ASL, LRL, ALR, logical shift right. What is ALR? It is supposed to be ASR and ROR mnemonics are strongly encouraged because it results in code that is much easier to read, debug, and maintain. Multiply operations with overflow, memory overflow. Multiply operations with overflow. These four instructions perform multiplication using two 32-bit registers to form a 32-bit result or two 64-bit registers to form a 64-bit result. Multiply, add, mod, mis, mnag, mnag, multiply and negate. I think this operation adds the carry to the number. This operation subtracts the carry from the number, and this operation negates the result. I don't know. Okay, store into this after multiplying this and this, and this is a specter. OP is one of mad, msb, mnek. OR is either multiply or mneg. Mul is alias for multiply and add, and mneg is alias for multiply and subtract. Both aliases use the zero register for RA. That makes sense. Mul when I add nothing. Oh, so after multiplying the contents of this and this, I can add the contents of this register or subtract the contents of this register. Or Minag is alias for MSB. Sub, sop, sop. Multiply. What does it do? Multiplies the contents of Rn and Rm and save them into Rd. Mad Muds. Madhya Pradesh. Okay. Um, multiplies Rn and Rm and adds the value Ra to them. Multiply and add. Multiply and subtract. Oh, it does not subtract from this. It uh, does not subtract this from the multiple of this. It subtracts from this the product of these. That makes sense. Multiply operation with 64-bit results. Cheat. Um, mm, small, 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 long. Why is the S signed and signed? These instructions perform multiplication using two 32-bit registers. You know why I am studying the assembly language? Because I have a book about things that I want to read, and in the introduction itself of that book, there was some assembly language. So I wanted to understand what is going on, and this is the book, Hacker's Delight. Yup. Ah, ah, yeah. Yup. It is really hard to get it right. Hacker's Delight. This is a recommendation by CS50. Good book. Ah, yes, I guess you read the whole thing uh, just now when I showed it to you. Now, I'm Chainsaw Man. Mm, hey, 16. Now, multiply operation with 64-bit results. Okay, how long is this chapter? 4.2.6, then 2.7, where operation with 128-bit things, and after that, division operations, okay, then comparison operations, okay, and then conditional operations, okay, 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 okay. Then special instructions at page number 104, and we are currently at page number 93. I guess we won't be able to complete 4.2, but at least let's complete the division part. Okay. Okay. These instructions perform multiplication using two 32-bit registers to form oh the contents of two 32-bit registers to form a 64-bit register to form a 64-bit result. Okay. Signed long. Signed multiply add long. Signed multiply subtract long. Signed multiply negate long. Unsigned multiply long. Unsigned multiply add long. Unsigned multiply subtract long. Unsigned multiply negate long. Multiply negate long. Yep. They are the same form as the previous multiplication instructions in section 4.2.5. That seems like a version of some product, except that they only use 32-bit operands, which are signed or unsigned, extended to produce a 64-bit output. To produce a 64-bit output, save into the XD register after multiplying the contents of this, add this, and then add or subtract this from this. Add or subtract from this. OP is a non-alias instruction. Non-A is alias. No, non-alias instruction. Okay, which is uh this add add or subtract long or signed or unsigned. And alias instructions, that is they can be achieved. The results of these instructions can be achieved using these instructions. And here we have multiply, multiply negate, signed, unsigned, and all are long. Sign extend this, sign it extends them, okay, and then multiplies them. Interesting. Oh yes, of course, it extends them by adding zeros to the front, and it does sign extend them to keep their value, to keep their sign. That is very beautiful. And it directly multiplies them when they are supposed to be unsigned. Only keep their raw value. Okay. Um, small, small sign multiply long and sign multiply subtract long. The contents of this and this will be multiplied. The contents of this, which is a 32-bit value, will have will be extended by sign. That is, if it is positive, then the 32 most significant bits in this first register will become 0, and if it is negative, then they will become 1, and then the same thing will happen with this, and both the values will be multiplied and stored in the 0th register. And in here, the value that is stored in 20th register and in the 21st register are multiplied directly without extending, and then it is subtracted. The result is subtracted from whatever is the value in the ninth register, and the resulting thing is stored in the 0th register. Multiply operations with 128-bit results. That is quite a trick thing. Signed and unsigned multiply high calculate. Signed and unsigned multiply high calculate the upper 64-bit of the 128-bit product of a multiplication between two 64-bit numbers. Okay, signed and unsigned multiply high multiply high. What does multiply high calculate? Means the upper 64 bits of a 128-bit product of multiplication between two 64-bit numbers. The lower 64 bits can be obtained using the mul instruction. Smulha, smulha, umulha. Okay, signed multiply high, unsigned multiply high. Operation can either be signed multiply high, not long, high, and unsigned multiply high. By high, here multiply high, they mean multiplying 64-bit values. To get a 128-bit result, that is high, pretty high. So this smooth command first extends the content of xn register, then it extends sign extends the content of xm register and multiplies them and stores the most significant 64 bytes into the XD, and umul does not extend them, just multiplies the raw contents of this and then stores the most significant 64 bits, sorry, into the XD register. Examples of mul and smooth, just raw dogs the multiplication of this, and the value stored in the first and the second register and stores the result in this 0th register. And smooth sign extends the value in x in the first register to get a 128-bit value, and also the same thing is done to the contents of the second register, and they are multiplied and the result is stored in the first register. The following example shows how a C program and oh yeah, I will see the C program and then try to write the assembly program, and then AArch64 assembly program could implement a simple command line tool for multiplying. A command line tool for multiplying 64-bit unsigned numbers without rounding or truncating the result. Multiply 64-bit unsigned numbers without rounding or truncating the result. To change the program to work with signed numbers, the only change needed for the Arch64 version would be to replace the umulh with smulh. Okay, what does this do? Okay, it states that there is a function called long multiply which returns unsigned 128-bit value, integer value, and it takes in unsigned 64-bit value, that is x, and an unsigned 64-bit value, that is y, and multiplies them and returns. Well, it first typecasts them uh, into 128-bit values and then returns the result. Reads two unsigned longs from standard and uh, reads two unsigned longs. Enter number in hex in here. Okay, get the value here, print the number, enter a number in hex to get the second value, and then we have a number product which is long multiplication of x and y, and its data type is this, and low is the typecasted 64-bit version of the product, and then the high 64-bit values are the thing we get by first shifting the product to left 64 bits, so that in the in the right 64 bit values bits contain the most significant 64 bit, and then we can typecast it into a 64-bit integer, and then we print the result. The first value into the second value gives this. Oh, gives this and this. Hmm. And then return 0. Now we have to write the arch function for this. Okay, we got this. And chapter 4 dot s. First, we comment all of this, then paste this. I don't understand Vim micros yet. Simple. Now I have to write an assembly code for this C code. That is good. Okay. But before that, let me go to the washroom. Not to see the answers, but you know, a man has to go when a man has to go. Yep, I have to be of the screen, right? Around it seems good. And I have something to eat, actually. A laddu. Yes. Now we can convert this. Ah, just press ZZ and the screen centers itself. Now in the dot data section, I have to get two uh, memory locations to store the result, to store the return value of the scanf function, right? So first one, let's call it x long, and it will contain a 64-bit value, that is double or d word. Is that double or d word? It is in data load store thingy. Is it double or d word or double? What is in second chapter? Probably. Yep. Byte, 2 byte, half word, short, long, quad, quad. Okay, none of those. So it is a quad. And then what do I have? What am I storing the quad? Zero. Initially it is zero. And wait, I don't even have. I can store zero. Okay, that is long. Okay, and then y long will also store a quad, which is zero. And then their result mul long will also store a quad, which is also zero right now, currently. Is that all the data that I will need? Nope, the low 32 bytes. Low will also be a quad, and currently it stores zero, and high will also be a quad, which is currently zero. And now in the dot text section, I define a global thing called main and aligned by 4 bytes, 2 to the power 4 is 4. And then I define the address of for the main thing, and that is it starts first by storing the frame pointer and the link register contents onto the stack. That is not a store. Yeah, store pair x29 and x30 into the stack pointer by decreasing the stack pointer by 16, pre-decreasing it. And then yes, after that I want uh, yes, I have to get the value, the address of the x long, and I think I can just by storing the address of x long, I can work with all the addresses. Let's say I want to ADRP get the address of page for into the X, no, not into the X long, but into the let's I will be using third register, no particular reason, just no ninth register, no particular reason, ninth register for this, and it will store the page offset of the X long register, and then I add to the contents of the 9 the page offset of the X long. Now I have the address for this and this. So now I have to call. Wait, where do I have to give the address? In the zeroth register to save it. Yes. So I will be moving into the zeroth register, the value in the ninth register. So I have the thing, right? Yes, this will be good. And then I now in the zeroth register I have the address of x long variable of the x long label. And now when I call um scanf, no shit, that is supposed to be go as the second parameter, the address. The first one has to specify what is the percent DL thingy, right? Like here, right here, scanf percent LX long extra. That is just a 64-bit number. So I have to specify the, let's say, format. Ah, shit, I am stupid. What is what is K doing here? Okay, and now in the format I store a ASCIIs. I don't know. I think ASCIIs would work. The string percent LX, and now I need to get the address for this, which I will be storing in. I can use add to store the result in the 10th register. The addition of this register and the immediate value. Wait, how long is it? The immediate value. Uh, to get to this, I will have to add one, like step 8 bytes once and twice, thrice, w- 1, 2, 3, 4, 5, 5 times. So 5 and left shift, logical left shift. Yes, by 5. No, by 8. That seems to make sense. Now in the 10th register, I have the value for the FMT thing. Now I don't want to store this, but this here. And now how can I pass the second parameter? By adding it to the stack pointer. Move, no, store the value in the store the value in the ninth register into the memory location whose address is at this stack pointer. Then call this, and then after this I should have at the x long memory location the value in the x long memory location, the value that is given to me by the scanf function. Now I want to get the second number. For that, the zeroth register is fine, but let's just in case, because now I have the return value for the scanf, which could be 0 in that register, in the zeroth register. Now in the first one, I have to get store the value for the format string, and in the stack pointer, I have to store the value of the ninth register plus something. So um, shift the value. No, 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 no. Let me do some adding, add, and store in the 11th register, right? In the 11th register. Makes sense. In the 11th register, store the value of the ninth register plus 1, which is logically left shifted 8 times. Now the 11th register should have the address for while long. Now I have to give that address, update the stack, the memory location at the stack, at the top of the stack, not by 9, but by the value, the address that is in the 11th register, and then call the scanf function. That seems to make sense. Now I should have in the xlong thing, in the xlong memory location, I should have the first value that I want to multiply, and in the ylong memory location, I should have the second value. Now, what do I want? I want to multiply them. I can make a function out of it, right? Now I can just directly do the multiply logic, right? Yeah. What will it do? Hmm. Unsigned mul hi. Is that it? Umul. Yes, that is it. Uh, the but first I have to load the contents of x long and y long. Yes, and where do I have the addresses? The address for x long is in the ninth register, and the address for y long is in the 10th register. So let's use the 0th register to store the result, and the 10th register to store, and the 10th register no the 0th register, 0th and first register to store the most and least significant bytes, and the first and the second register, or maybe just arbitrary, let's use the third register to store the third and fourth, to store the most significant and least significant bits of our 128-bit number, and then let's use the fifth and the sixth register to store those two 64-bit values. So I want to load into the fifth register the value that is at the value whose address is in the ninth register, and also load into the sixth register the value whose address is in the 11th register. That makes sense. Now I have to multiply these two numbers and get the most significant bytes in one register and the least significant bytes in another register. How can I get them? Well, if I can get the most significant bytes, yes, that would be easy by doing. unsigned mul high and storing the result in the third register and multiply the contents of the fifth and the sixth register. But how do I get the least significant bytes? If I multiply long, but that, how can I multiply two? Okay, I know that multiply high gives back the most significant 64 bits after multiplying two 64-bit values. Uh, 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 uh. So, how can I get the least significant bit? If I left shift it, the result by 64 bits, I will get the least significant bit after multiplying, but how do I left shift the result? Ah, shit. Wait, let me see. Extend and multiply gives the most significant bytes. Yep, this gives the most significant bytes. And how do I get the least significant bytes? Least when I multiply two 64-bit numbers. Use this uses to produce a 64-bit value. Ah, but I want to use two 64-bit numbers. Long will it takes raw dogging the multiplication. Yes, I can just raw dog the multiplication. That also makes sense. Yep. So, to get the least significant bytes, I just multiply and store the result in the fourth register, and then multiply the things in the fifth and the sixth register. Now, I have the most and the least significant bytes. The third register has the most significant bytes, and the fourth register has the least significant 64 bits. I have been replacing bits and bytes. That is a mistake. Now, I want to print them to the screen. So I have to define another format thingy, format 2, which will definitely store an ASCII, which will be this equal to this. Okay, which will be equal to this. And yep. Now I am before calling printf, I have to get the address of this thing into the zeroth register. So address page, or I can raw dog. Like I can calculate it using the offset thing, right? Add and store the result in the zeroth register. Add to the contents of the 10th register, which stores the value, the address of the format thing. And I want to add 64 to it. Add the immediate value 64. No, no, the immediate value 8. Oh shit, I messed up there, didn't I? If I multiply by 8, so 1 becomes, uh, if I multiply by 8, no, if I left shift by 8 times that is 2, that is 2 power 8, which is a lot. It's like 128, so this is wrong. I don't have to left shift it by 8, but by 3, because left shifting something. Here I am using 5. So for 1, I want 8 to be there, and for 1 to become 8, I have to left shift it by 3, which means multiplying it by 8. And how do I get that? I get it by 2 power 3 is 8. Now here. Yeah, yes, 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 yes. Now in the zeroth register, I have the address for the format, and now I have to provide the inputs, shit, three inputs on top of the stack pointer, onto the stack. Yes. So the first two are the four inputs I have to provide. Okay, 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 okay. The first two are five, six. No, the first two are five and six, and then we have third and fourth registers. So I have to store them. Are store pair of x5 and x6, and then this add the stack and decrease the stack pointer by 16, which is, yes, which is increasing the stack, and pre it pre like pre. So before adding to the stack, I update the stack pointer, and then I store. This should work. This should actually work. I might just be messing up. But let's see. Stack pointer and update it by 16-bit pre increment. Okay, and now I have all the things in the zeroth register. I have the address for the string and then the parameters on the stack. Now I just call the printf function, printf, and now after that I move into the zeroth register the value 0 and then just return. Now this should work, I guess. Uh, this oh, this might not work, and that would also be okay. Okay. Hmm. Unrecognized instruction mnemonic. What is strp is nothing else. It is stp. And what are the other things? Yeah, the clever address finding thingy. Okay, and chapter 4 dot s. Where is strp? Here. And where is the thing I was boasting about? Okay, so 5 8 I can directly write 40 here, and for, so this is stupid. I can directly write 8, and this should, okay, now it wants me to enter a 64-bit value. Enter this. Yeah. Segmentation fault in assembly. Shit. Chapter 4 dot s. Segmentation fault in assembly. Shit. That is tragic. Why? Um, the time that I call the first scanf, it works. Then, hmm, then shit, I not store this value on the stack, and then I call the function, the scanf function. So, okay, I am trying to figure out how to give parameters to the scanf function, because I have been giving parameters to the printf function through the stack. Only the first parameter goes into the zeroth register, and The second and third parameters, I am giving them to it from the stack. Well, I can see it directly if I uh, find the assembly for the C code, but let's see how this is. Why am I getting a error? Okay, I overwrite the value on the stack. Should I just increase it afterwards? Or just before minus 8, like a good boy. Okay, and then minus 8, just like that, and then here. Let's see if this works. Well, it compiles. Okay, bus error. Now the bus doesn't move. And chapter 4.s. And where am I messing up? I messed up with the stack pointer. Should I be directly working with the stack pointer? I am a noob. I am a noob. Oh, okay, let's try to give arguments to it through uh, I'm storing the address at the stack pointer. Let's try to give arguments through the registers, right? Just like that. And instead of this, just like that, and everything else will be the same. And I did work with the stack pointer here. Okay. And mhm, okay. I won't be thinking too much, and yes, I should have. Should I? Why am I using store? Chapter 4. I don't have to be using store for moving. I just use move in such a case. Move. And okay, let's see if it works now. Well, it compiles. No error till now. Now error. Segmentation fault. Okay. So why am I getting a segmentation fault? Is it because when the scanf function is trying to save the result at this address? Okay, let me try to get the address properly this time. Right, and I want the address in the 10th register, therefore I will go in the 10th. Yes, I want the address in the 10th register. So address of y, no, not y. I already got the, shit, fucking hell. Yeah, uh, that should work. That should work, but let me just try it. Um, in the 10th register, I am getting the value of FMT. First, I get the page address and then add and save to the 10th register, the value of 10th register plus FMT page offset instead of this. And here also, I have to do this. I have to do the same thing. ADRP, get the address page into the 11th register for y long page and add and save to the 11th register, the value in the 11th register, and wh- why why long why the long face, why page of this should work, I guess. And here also I want the some address. Wait, I want the address of what is in the 10th. In the 10th, okay, I want the address of fmt2 of fmt2. Okay, okay, I want the address of fmt2 in the 0th register here. Okay, so address of page, save it into the 0th register of, and whose page, fmt2 um, at page, and add and save to the 0th register the value of fmt2 page offset and ah, error. Okay, it compiles. Now error. Okay, it works, and now I'm expecting to see error. Hopefully, I will see some error. Segmentation fault. Okay, I will try and figure this out today, and tomorrow I will explain. Ah, shit. Segway. Yeah, I'm seeing the error. Segway took 7 seconds. And Segway bus error, Segway something something. Mhm. Okay, and so let's end the stream at our failure. And today, tomorrow, we will win the battle.